Hi everyone, my name is Oleksandr and I work here at Facebook Seattle on the app efficiency team. And today I'm going to talk about the MobileBoost. A short agenda of the items that we are going to talk about. We will firstly talk about what does a perf mean, where it actually matters, and what do we mean when we are talking about slow mobile apps. We are going to talk what is this framework about, why did we build it, and what's the reason for doing it. We are going to talk about most common optimization techniques that we can use on the mobile phones that are actually not tied to the actual product that we are talking about. And finally, what kind of protections and measures can we put making sure that our optimization are running smoothly and carefully. Good. So when we are talking about performance and when we are talking about mobile apps or be it web apps, when we say that the app is slow, we not necessarily mean that the app is slow overall. We mean certain particular interactions that we are talking about, being the app startup, being transition between different surfaces that we are having, or the scroll. And people have different expectations for all of them. So for example, people can wait, typically for the mobile app, people wait for up to 5 seconds when the app start is fresh. If it is longer, they will say, hey, the app is broken, I don't want to use Facebook or whatever the other app is, I want to move on. If it's faster, then great, they're actually using it. If it's navigation, depending on what type of navigation we are talking about, hey, if you're playing the video, people expect the video to be downloaded, and they kind of accustomed that, hey, it can take longer time. We have different interaction classes that we are talking about for them. So we tell that a given interaction is responsive if it took less than 1 second, it's fluid if it took less than half a second, and so on and so forth. The main idea is that we try to bucket it rather than look into one single number and just tell, hey, it runs fast or it runs slow. People will have different expectations, and we might want to tune our interactions differently depending on what people expect. A very similar stuff is scroller animation performance. So a lot of mobile devices, they run at a refresh rate of 60 Hz. So you have a frame time of 16 milliseconds. And you have your code that needs to be finished to render a frame even less than that, because it's not only your application code that's running that time, that there will be a framework code that runs there. And if it takes more than 16 milliseconds, you'll see a tiny glitch that you're doing when you're doing scroll or when you're doing animation, and people notice it. By notice it, we see a very strong correlation between performance and engagement metric, right? So if the app starts too slow, your visitation drops. If your scroll performance is not that smooth, people start scrolling less, they watch less video, they put less likes, and finally they give less money, which is the most important. So with that in mind, when we are typically talking about the interaction, we have the bounds of it, right? The interaction starts when people do something with the app. They touch with the finger on the launcher icon or on some buttons, or they try to flink on the screen or do something on that. And it typically finishes when everything that's necessary to be done is done. So UI is drawn, and UI typically means all the controls that you're having and the images, they're fully displayed. People are able to have a satisfaction of what they did. And it is ready to interact. So if you try to press on some button that's shown on the screen, it's actually responsive, right? You're clicking on it, you see a touch feedback, and you actually can do something meaningful with it. And there can be many different bottlenecks if you're talking about primary device resources that are happening with it. So we can be bound on network, right? You want to fetch some data from the network, and you want to make sure that your network request is executed as early as possible. We can do some CPU cycles. We can do some disk I/O work, be it reads or writes. We can allocate memory on some of the systems. We can run garbage collections. And it all depends on very different factors, right? So if we are talking about mobile phones, historically we believe that CPU is one of the biggest bottlenecks, but disk I/O is actually a big bottleneck, especially if we are talking about more older phones, more low-end phones in the developing markets. We really need to keep in mind about combination of all of them and seeing what's there. So the MobileBoost, what is it about? Is looking into all of those primary device resources that we are talking about and just try to magically make them faster. We'll listen when the interaction starts, and we'll listen when the interaction finishes. And we try to look at what's actually spending most of our time on the disk I/O or on the memory or on the network, and try to improve it. And we enable this optimization. And whenever it finishes, we disable this optimization. So the reason why we come up with this idea is that we know inside the app what's important to users. We see where they spend most of their time is, where they press the buttons, what is their typical pattern. And It also makes sense to, instead of just going to product and fix all the issues that they're having, it makes it way more robust. We don't need to come to 30, 40, 100 different product teams and tell, hey, you have this performance issue, please fix it. Here's the wiki page or example of the code that you can be doing. We just fix it for them. You just tell us when your interaction starts and when it finishes, and we will automatically listen for it and try to apply this optimization. So with that framework in mind, and I already talked about what kind of optimization can we have, let's talk about some of them. So I already mentioned that the disk I/O is one of the very big bottleneck. On the very old phones, one page fault that you are having can have about 0.8 milliseconds. And if you're having a lot of code, that means a lot of time spent in reading the code. For the Android mobile devices, typically what we're having, we need to read code in our Java classes. And we already mentioned that we store it in the DEX file format, which is the bytecode format for Android, and it's memory map file, so we need to fold for every class that we're having. So if you have an interaction, it starts and ends, you have a critical path, you have many classes that are happening there, and you need to read the code for all the classes that we are having. And that's being said, hey, that's what you need to do, right? You want to do something, you need to load the code and execute it. Is there anything that we can be done better? Turns out, yes-ish. If we know all the classes beforehand that we are executing there, we collect them somehow, we can actually, at the very beginning of the interaction, spawn a background thread and try to load all those classes in the background thread to the page cache. So then when our actual critical interaction happens, and say we try to fold the classes from the UI thread that can be very slow, they are already in the page cache. They are already loaded, and we don't need to spend any significant amount of time trying to follow them. The tricky part is obviously collecting all of those classes. Luckily, a lot of our interactions, they have only one critical path, so there is no bimodality or some weird stuff that would make it really hard. And also very compactly representing it, right? So we want to make sure that, hey, this background thread that's happening, it knows what classes to load, it knows how to load them efficiently. Cool. Another typical bottleneck that we are having is CPU. You can run a lot of code on your CPU. And on mobile phones, a lot of the architectures, they have heterogeneous core, right? So we have a big core, which is more powerful core, typically use more battery. And there's a little core, that uses less battery, but it's less efficient. So one of the stuff that we are trying to give hints is to, hey, if you have a very important thread that we are talking about, we know that it is important for the interaction, we suggest it to run on the big core. Or if it is very unimportant, then we try to run it on the little core. We are not trying to turn on or off cores on lines. We don't have this capability on Android. We just give hints with thread affinity. And a very similar stuff, we try to give hints to the scheduler of like, hey, if this thread is very important, run it on the higher CPU or run it at a higher priority. This is more Java-specific item. We do a lot of memory allocation. Memory allocation can trigger the garbage collection. And by itself, the way Android open source system is designed, it doesn't know when to run the garbage collection. It just listens to all of the allocations that are happening. And if you're close to the heap limit, we say, hey, it's about the time, let's run garbage collection. It can be brutal, especially on more older Android OS version. It can have about 100 milliseconds of time to be done. As well, on the older Android system, it stopped the world. We need to suspend all the threads to execute it. So our interaction just ends, and that's not fun. If you could only give a hint, hey, this is very short-lived interaction. We don't necessarily need to run a garbage collection right now. But in a second or two, hopefully we will be able to run it. We can speed up our interaction way better. We need to be very careful with it, right? If we're running very close to the heap limit, if, hey, the garbage collection is actually necessary to be done at this moment, then we just bail out and continue with the regular flow. We also make sure that when interaction finishes, we actually force it, right? The interaction just finished. People saw some screen, so they are not likely interacting with it in the next few hundred milliseconds or so. So we use this window of time to try to run the useful work that we are having. Cool. Going back to disk I/O. A lot of the interactions that we are having, say you're scrolling or you're trying to open something like notification, your messages, or whatever it is, they don't necessarily need to have synchronous writes that are happening there. But your application is actually using them. And those writes are, typically most of the time is you're writing something to your cache, be it the images that you just fetch and display to the people. You want to save it to the disk cache and making sure that it's used later in the future in case the image is reused. You're doing some login, and that login will be later asynchronously uploaded to your server. So you don't necessarily need to do it straight when the interaction happens, right? You can wait, very similarly to how garbage collection is done, just till the very end and make sure that you have it there. One of the other stuff that we are trying to do is that we try to avoid explicit fsyncs because on the Android implementation, fsync not just flushes the file handle that you're given to it, but it flushes everything that's inside the page cache. So it can be very slow when we are trying to do it. As well, we're listening when interaction finishes and we tell, hey, right now you can do all your writes, you can do all your caching and whatever is important for you. Cool. So we talked about some of the optimization types that we are having. There's much more that we are doing. This is just more to showcase about different levels that we operate. We look at the actual primary resources rather than we try to go and fix the actual product code. Why just not we enable them anywhere, right? If they're good, if they're just working great, why not try to enable them for all interaction, all kinds of different optimization? So there are a few reasons. So first of all, our interactions that we are having, they can overlap very easily, right? So for example, if your interaction is trying to type a message and you type very fast, one after another can quickly overlap. If you run your optimization for a really long time, that can have a very bad consequences. So for example, delaying garbage collection for a really long time can your app. There are risks. Some of the optimizations are actually not that safe and important. We talked about delaying disk writes. And the keyword there was non-critical. So if for your interaction to actually succeed, you need to do the disk write. You actually do not want to enable it all the time. So you want to be careful about what you're doing. When we are trying to operate on the primary device resources, we want to make sure that we are very careful with usage of it. So I mentioned about using the background thread and using and preloading the classes. If you preload a lot of classes, we can still continue in the preloading even when the interaction finishes. And we're actually trying to hamper the disk when the user is already doing something else. So we try to put the constraints on the resources that we are doing, not abusing them and making sure that we are having them right of time. So with the overlap, we are trying to be very diligent about what scenarios are we actually tracking for. So we know we have this list compiled based on how much time people spend on them. And we just control them server side, making sure that, hey, we know where the optimization is turned on, which is turned off. If in case there's overlap, there's something wrong, the instrumentation is broken, we have inside the framework listening to those overlap and just enable it for the first version of the event. We typically have a timeout in case the optimization runs for a really long time, longer than 5 seconds. We say, hey, something is wrong. We missed some use case. So we just turn it off and watch those timeouts. We limit the amount of primary resources that we are trying to use. So depending on what of the stuff that we are trying to optimize, hey, we say don't use more than 1,000 classes or don't delay more than 1 megabytes of data and so on and so forth. And finally, on a lot of the performance optimizations, we are trying to, when we roll them out, we do a lot of A/B tests. So we roll them out to a small amount of population based on the assumption that we have, watch out the performance data, and then even after it is rolled out, we typically try to pay attention for, hey, how much effect does it have and does it help for us? Maybe some assumptions just changed and this performance optimization doesn't make sense anymore at all. Cool. So that's about it. We talked about what's important for the performance and what is actual critical interaction and what we are trying to tackle on. We talked about different types of buckets of optimization that we are having and guardrails that we can put to run them smoothly. Thanks. If you have any questions, please ask.
Thanks. I'm Lee. I'm from Google. You mentioned these instrumentations. This is something that developers put in saying this is going to be an interaction. What kind of metadata comes with these? Can they say what latency class they are expecting or other things like this?
Yeah, so typically what product developers do, they just tell, hey, this is my interaction start, this is my interaction finish. They can attach all kinds of different metadata, like, for example, which surface you're coming from, are you hitting cache or are you hitting the network scenarios and whatever it is. But they're literally only, this is more on the framework level. We can't get this information by themselves. What we try to minimize the amount of information we require from developers, because then it's a cognitive overhead. They're like, oh, in order to integrate your framework, I need to do A, B, C, D, E. We literally just ask them, hey, tell when it starts, when it finishes, and then we do everything for them. So we try to reduce this info.
They have critical context. I'd like to know a way to get that context that they have in their head.
So to be precise, most of the product developers don't, right? They kind of feel like, oh, probably I spend most of my time waiting for my network request to come back, right? But their assumption might be wrong. Maybe they just have a lot of code that they need to read from disk, right? Or vice versa. They say, hey, our surface is very big, but actually they just execute a network request like 1 second later after they touch with their finger. So those assumptions might not be right, and relying purely on the product developers for them might not be the best decision.
Hey, I had a question about one particular topic that you touched upon, using thread affinities. In my experience, I've seen that the kernel especially doesn't like when you affinitize threads, especially with concerns about scheduling and power consumptions. Most of the optimization at the kernel level is wouldn't be viable for us to use when we start playing around with these things. Have you faced any situations?
Yeah, so we are very careful about stuff like battery, and making sure we go ahead and do something that's prohibited. So for one, no, we do not turn on the cores online or do something that's very risky. We only have a hint, right? Hey, if the big core is already online, and we know that this thread is very important, we just say, hey, run on the big core if it is online. But if it doesn't, no, we don't try to do it, because we can easily regress battery, and that can be having bad consequences.
Awesome. Thank you so much, Oleksandr.